Welcome back and to actually a new topic. And this is something which will need to bake into our programs. And this is a topic which is very important in Monte Carlo sampling. And it's called importance sampling. And this is something which hopefully will give us better results. So what I want to do first is actually to give you a top-down view of what we need to program. And then we are going to retrace back and bring in all the basic small ingredients which are needed to understand why we are doing what we do. So the main topic today, after a quick repetition, where we're going to use the whiteboard about Markov chains from last week, is actually about the Metropolis Hastings algorithm and something which is called importance sampling. And I will try to guide you through some of these elements. And for next week as well, because this topic will continue next week, is to discuss in more detail something which is called the Fokker-Planck equation and the Langevin equations. So these are two important equations in stochastic samplings. And for those of you who are familiar with machine learning, you will see that these kind of methods are actually used widely in the application of Markov chain Monte Carlos in generative methods like variational autoencoders, diffusion models, etc. So the basic equation which we are going to deal with, because a Monte Carlo calculation based on Markov chains is based on the physical process of diffusion. Now, the thing we are going to bring in is a way to guide the random walkers in space according to the probability distribution which we have chosen, which is the wave function squared in quantum mechanical calculation. This is something which will replace what we call for the brute force or the simple Metropolis algorithm, where we simply let the random walkers jump according to a prefixed step size. This leads to a kind of rule of thumb where we say that we accept roughly 50% of the suggested moves. So this is like you tossing a coin. You suggest a move and you accept it with something like a 50% likelihood. There is nothing beyond that than just tossing the coin. Now we want to do some more intelligent jumping so that we don't waste, let's say, 50% of the suggested moves, because it takes time to evaluate these things. And if you think back to the Metropolis algorithm and the ratio between the wave function squared, this is actually an expensive calculation to perform. So today we will focus mainly on importance sampling, but I wanted to guide the eye a little bit so that you see what kind of ingredients we need to program. And then next week in particular, we will actually derive the Fokker-Planck equations and the Langevin equation, so that you see where these equations and the quantities you need to bake in actually where they come from. So importance sampling is based on us suggesting moves using what's called the Langevin equation. This is a differential equation, which is actually based on Newton's equation, where we have a stochastic term. And then we have this function f, which if you look back at the diffusion equation, you can think of this as a drift term. So diffusion itself as a physical process has a kinetic energy term times a diffusion constant. So the first term is a kinetic energy term. And then you can think of your particles moving in a field. And that field could be a gravitational field, which could be this f. Now this f is going to be replaced by our trial wave function. And since there is a derivative here, that means that we're going to need to calculate the gradient of the wave function. So this is a technicality which we will discuss in more detail next week. But it means that our random walkers now are going to be given by a new position y, where we have a previous position x, and then there is this diffusion constant times this quantity, which we will call not a gravitational force or force field, but we will call it the quantum force because it's based on the quantum mechanical wave function. So that's just a name. And then there is a time step. So this follows from actually the integration using actually Euler's method for integrating this equation. And there will be some random noise where with this epsilon is a Gaussian variable. And there is a square root of delta t, and we are coming back to the derivation of this one next week. But now I'm just stating the equations which we will need to plug into the program. So instead of having x plus a random numbers multiplied with a step, we are now going to let the random walker to jump according to a specific probability distribution. And this delta t is normally is now a parameter, and you would typically choose it between 10 to the minus 3 to 10 to the minus 1 or 10 to the minus 2. If you make this delta t too small, then you will barely move. If you make it too large, you will be jumping away from where the distribution is non-zero. So this is the basic idea. And I'm now just going to run quickly through things because we will bring this back next week. But what we would need then is this quantity here. So this is why we in the project have an exercise where you are going to calculate the gradient of the wave function. Now, this is something you will need irrespective of whether you do important sampling or not, because you need the gradient in order to calculate the second derivative. So you would have to calculate that one anyway. And this quantity, which you see here, is normally called the quantum force, and we're going to do the derivation more properly next week. But today, we are going to discuss in more detail what important sampling means and why this trial wave function have a specific form. So at the end, what we are going to do then is to change our Metropolis algorithm to something which is normally called the Metropolis-Hastings algorithm, where last week, what we did was to take this acceptance ratio to just be given by the ratios between the probabilities. But now we are going to have a transition probability, which will be modeled according to this Green's function, which is the solution of the Fokker-Planck equation. So there are many small steps here, which we will try to build up your understanding of today and next week. So this topic is something which normally we spend 2 weeks or 2 double lectures plus a little bit more, so that you can get the basic mathematical understanding of what these ingredients mean. And this means that instead of you having the wave function squared in a new position y, you now have a probability distribution which tells you what is the likelihood of jumping from x to y or going from y to x. I'm going to bring back the Metropolis algorithm in just a few moments. So there is a code here, and this is the example you can look at on how you can implement this important sampling. And the code basically is the same as we had before, and it's applied to a 2-electron case. This is slightly different from what you have in the project, but these are 2 electrons which are moving in a harmonic oscillator trap, but interacting with a Coulomb interaction. So the problem is slightly different, but it's almost the same if you take away the Coulomb interaction between the 2 electrons. And then you will have a harmonic oscillator problem. Now, a harmonic oscillator problem in 2 dimensions, as it says, it's a 2-dim quantum dot. So quantum dots are very important systems in semiconductor physics, but they're also systems which are used as platforms for quantum computing, because you can isolate single electrons in small spaces between layers between semiconductors, and you can treat this electron and their quantum mechanical states as qubit representations. So quantum dot systems is one of these very popular platforms in semiconductor physics and nanotechnologies, which are used as candidate systems for making quantum circuits and quantum gates for quantum computer. So they're actually quantum dot quantum computers. So this is the system which we have here is something I will come back to this towards the end of the lecture. And then we will see how we can implement this feature. So this is a feature which you will need to implement, and you will need this quantity, which is the quantum force. This is a kind of naming which is used, and that is the gradient of the wave function. And that quantity F enters the calculation of this transition probability. So at the end, you need to calculate this object, include that one in the ratio for the metropolis test. So we are coming back to this, okay? So this is more the top-down view of what you need to code. So one way you can think of this, if you want to get started with coding, is to actually look at this example and bake in this function, but then just leave out the basic understanding of it till we've gone through the mathematics of it. So this is the top-down view of what we need to do. So what I want to do now is actually to go through some of the basic elements of importance sampling. And that's where I'm going to switch to the whiteboard so that we have the basic mathematical understanding of what that is. So let's switch to the whiteboard. So what we are going to need now is first a quick reminder from last week. And after we've done this reminder, we are going to look at what importance sampling means mathematically and why we should do it. So if we now do a very quick reminder from last week. One of the essential things which we looked at was the Markov chain Monte Carlo. So we have a Markov chain where we have a probability, Wi of t, and that is, so this is a probability distribution, and that is given by the sum over all the states you can be in. So you could think of this J as something which runs over all the positions in space where your object can be. And then we have this transition probability of going from J to I, and multiplied with the probability of being in a state J at a time t prime. So this is essentially the definition of a Markov chain. And it's the basic building step in a Markov chain Monte Carlo procedure. So when we take the limit of time goes to infinity, what we have then is that this probability distribution becomes a stationary probability distribution, and we have no time dependence any longer. Now, in principle, what we do then is that when we look at this probability of going from a state J to a state I, so what we call the transition probability, so this is a probability which now is written with its uppercase letters. And this is normally a quantity which we don't know. So it's given mathematically by what we call a stochastic matrix, as we discussed last time. And in general, this quantity is unknown. We have a model for the probability distribution, and our model for the probability distribution is just the wave function squared. But the transition probability is unknown. That means that we, in a certain sense, can model it as we want. And the way we modeled it last time was to set up a quantity which we called the probability of making the transition, multiplied with what we called the acceptance probability. So you could think of this as being a probability which you can calculate for making a specific transition. So probability for a specific transition, whereas this quantity here is something which we call for the acceptance probability. So you calculate the probability of making a move, and then you have another probability for accepting that suggested move. Now, what we found then last week, when we used what's called detailed balance, so let's just put that up here again. So we have what we call detailed balance. which is the condition which has to be satisfied when equilibrium has been established. And we call this detailed balance. And in that specific case, what we have is that this probability distribution, or this acceptance probability, for going from a state J to a state I, is something which can be given by the ratio between the probability which we have being in a state Wi and state I and J, and this is then multiplied with this probability of making a transition from I to J divided by J to I. Now, one thing which we did last week, so let's just mark this one, that was that we assumed that there was a symmetry, and this is something which can happen, so that the probability of going from I to J, so there's a specific symmetry which we have imposed, and in that specific case, we end up what is normally called the simpler metropolis algorithm. So when we use that specific symmetry, then this leads to what we just call the metropolis algorithm. Now, the quantity which we have here, on the other hand, that is the ratios between probabilities, and that is a quantity which we can calculate, and that is known. Because we have chosen a model for the probability distributions. So we have chosen a probability here, which actually goes over to the wave function squared, the trial wave function which we have made, in a position Ri, with some parameters alpha squared, and this is divided by the normalization constant. And where we have this R in the domain where we have specified this, so D of R is now a collective container for all the positions of the particles. And this goes like C of T of R of alpha squared. That is our probability. And this is something which we can calculate. Although this can actually be a very complicated object, because if you think of you having 100 bosons in project one, and these are in 3 dimensions, then the quantity which you see here, this wave functions, is a 300-dimensional problem. So if you were to calculate that one for every move you suggest for the 100 particles, it means that you would have to evaluate something which is a 300-dimensional quantity. So I'm interjecting now a technicality, which is something you will implement in the codes, which makes life easier from a computational perspective. So when you are moving your objects, you can perform the metropolis test after you have moved. So if you have 100 particles in 3 dimensions, as I said, this is a 300-dimensional object. So you can move all 100 particles, you suggest a move, and then perform the metropolis test. That means that you have to evaluate this for 300 positions. 100 particles times 3 dimensions, that is a 300-dimensional object. What you're going to see now is that you can simplify this with something which is equivalent, where you move one particle at a time. When you move one particle at a time, since many of these trial wave functions are going to be exponential functions, what happens then, if we move one particle at a time, is that we can simplify the calculation of this ratio. So let me just bring this up as something which is important from a computational point of view. So this is as an aside. So this is a computational technicality. So let's just take a simple example in order to illustrate this. So we can now move one particle at a time. So that means that suppose now that we have an example with a harmonic oscillator in any dimension. It can be 3 dimensions, 2 dimensions, and we have 3 particles. So let's just take an example here. So we now take a harmonic oscillator, HO, in 2 or 3 dimensions, in D dim, and 3 particles. So what I'm going to do then is to, when I calculate the ratio, so it means that this W1 I divided by Wj here is then going to be equal, if I use the harmonic oscillator, minus alpha squared. And then I'm moving particle 1, so I put a prime here. And then I just leave particle 2 unchanged and particle 3 unchanged. So I'm just moving 1 particle at a time. Then I divide this with e to the minus alpha squared. And then I have r1 squared plus r2 squared plus r3 cubed. So many of these trial wave functions have an exponential form. And you will see quickly why they often have an exponential form. Now, if you look at this ratio which you're calculating, if I were to move all particles and then perform the metropolis test, then I would obviously have to calculate R2 changed and R3 changed. If I look at this, on the other hand, this is nothing but e to the minus alpha squared of R1 prime minus R1 squared, because the other ones are the same. So the benefit of having a trial wave function of the exponential type is that it's easier to evaluate this ratio. If on the other hand, if you move all and perform the metropolis test, so you move all particles, then you would have to calculate e to the minus alpha squared, and then I need R1 plus R2 squared plus R3 squared prime minus R1 minus R2 and minus R3. Now, when you also include more complicated parts of the wave function, this often becomes much more time-consuming from a computational point of view. So moving 1 particle at a time, as you will see later, is something which is going to simplify many of these calculations. So when you are performing the metropolis test, you will find it more convenient to move 1 particle at a time instead of moving all and performing the metropolis test. So this is something you can think of in the code which I have, the examples. I just move all particles simply because the test I'm doing is just a simple case with 2 particles only. And then you will see that it doesn't matter that much. But when you're getting into many particles, then your wave function becomes a huge monster. And if you think of this case with 100 particles, which you're going to do in the project, and you have these in 3 dimensions, then your wave function, which you have to evaluate, is a 300-dimensional one. Whereas if you move 1 particle at a time, you can simplify many of these tests. And you will see that this becomes beneficial also when you calculate the metropolis test with importance sampling. So this was just a small technicality, which we're going to discuss a little bit more later as well. So what we need now, if we go back to what we had here, we need now to make a model for this function t. And this is what is the main core of importance sampling. So if we then look at importance sampling, what it's going to imply for us so importance sampling means here a model for this t I going to j. And in our case, this is going to be based on the probability which we have. On psi of t of r being in a position I with some variational parameters alpha. Any questions so far? So this is what the task is going to be about. Now, in order to get an understanding of why we do this, we need to look a little bit about the basics of Monte Carlo integration, and then ask ourselves, what is important sampling and why do we do it? And yeah. Is a model for transition probability. Yeah. So that means that your metropolis test now is going to change from the simpler one which we had. So it means that the metropolis test now is going to change to what often in the literature is called the metropolis Hastings. So we are going to have a model for this acceptance probability, which is still going to be given by the minimum value of 1. And then we have the ratio of Wi multiplied with this Ti going to j divided by Wj and T of j going to I. So we are going to make a model for this T. And the hope then is that we can get a more efficient sampling so that we don't waste cycles on points where the function we want to integrate is 0. Okay, so this is our main task now. And I wanted now to go a little bit back to some basics of Monte Carlo integrations in order to try to explain to you what important sampling means. Of Monte Carlo integration or stochastic integration. This is often a better word, stochastic integration. So let's take a simple integral, okay? So let's now say that we have a one-dimensional integral, I, and we are integrating from 0 to 1. So I'm just taking a simple integration limit. And I want to integrate a function f of x, d of x. But now I want to use stochastic methods to integrate that function. Now, you can actually, through something which is called one of the fundamental theorems of calculus, if you now think of the uniform distribution. So let's move on. Is it okay if I move on? So let us now introduce the uniform distribution. There is no specific symbol for that one, but I will just label that with a U. So we call this U. So I'm going to have X values, which are going to be sampled according to the uniform distribution. So this means that what we have here is a distribution probability. So let me just define the probability. So this probability P of X of dx. So this is a probability of finding a specific event X in an interval d of X. This is given by d of X when X is between 0 and 1 and 0 else. So that means that if I plot this probability P of X here, it is just 1 between 0 and 1. So this is just to remind you a little bit about the probability distribution, okay? Now you can, by change of variables, you can always rewrite these integrals. But the important point now is that if you look at the uniform distribution, if I take 1,000 samples, this should be distributed uniformly. So if we now say that we do M, which is the number of samples, or number of points which we pick, then if M is equal to 1,000, then we should have in a domain like, so that means that with uniform distribution, uniform PDF, then every slot which we have between, let's say, 0 to 0, 1, 0, 1 to 0, 2, etc. And all these, that we should have 100 points. Here we should have 100 points, etc. So that means that's what's meant with a uniform distribution, okay? Now, if you go back to the interval, which we are integrating over, if we look at this specific integral which we have, we can actually rewrite this integral as an expectation value. So if we now pick back this integral which we have, if we now go back and look at this I from 0 to 1 of f of x, d of x, we can actually write this with a uniform distribution as 0 to 1 of p of x, f of x, of d of x, because the distribution is 1. Now, the uniform distribution which we have, it's normalized, so p of x, d of x is also equal to 1. So if we use this result here, then we know that we can rewrite this as the expectation value of f of x. In general, an integral, if we now do changes of variables, then we will always have a integral like this one, which can be rewritten as an expectation value of some given probability. So this is also called one of these fundamental theorems of calculus. So we can actually rewrite an integral as the expectation value of a quantity f of x. It's very easy to see this if we introduce the uniform distribution. But we can change because the uniform distribution is defined in a specific interval here. But we can change this to other distributions because in general, what we will have is something which goes like from minus infinity to infinity of p of x, d of x equal to 1. And we also have important properties that these probabilities are always defined to be less or equal to 1. Obviously, they are normalized, the probabilities. The cumulative probability, if I now integrate from minus infinity up to a of this p of x, d of x, this is smaller or equal of the integral of minus a up to b of p of x of d of x, and where this a is smaller or equal to b. So this is the property you see here is normally called the cumulative probability. So that's the sum or the integral of all probabilities up to a specific point. I don't know how much probability calculus you've gone through, but the important aspect which comes now is when we are dealing with this type of integrations, because we are going to perform a multidimensional integrals with Monte Carlo sampling. So variational Monte Carlo, which you are going to implement, is in essence a stochastic integration of a multidimensional object. That's the basic essence of what we are going to implement. So there are two key topics here. One, we are normally not confined to an interval between 0 and 1. So that means that we can have something which is called change of variables, obviously. So if I want to use a exponential distribution, then I can relate that one to the uniform distribution. Now, there's a very important aspect now, and keep this in mind. And this is one of the reasons why we are doing this specific change of variables. Now, if you look at random number generators, RNGs, the basic RNG, which you find in essentially all implementations of random numbers, is based on the uniform distribution. So the basic algorithms are random number generators which generate numbers according to the uniform distribution. Now, if you have a Gaussian distribution in your calculation, you need to make a change of variables and go map from a uniform distribution to a Gaussian distribution. So we are actually stuck with this specific feature. So the standard random number generators, they are based on the uniform distribution. So that means that we often need to do a change of variables. So this is an important thing to keep in mind when we are doing these different operations which are coming now. Then the next topic is actually importance sampling. And then I will try to guide you and motivate you why importance sampling is this important. And hopefully the examples I'm going to show you will try to give you a better understanding of why this is an important feature. Now, let us look at the change of variables, okay? Let's take that one first. Suppose now I have a probability distribution with a variable y, py dy, which is given by the standard exponential distribution. So this is my probability distribution. And that means that the y, so let's call this example 1. So y then is defined between 0 and infinity. So that's my domain. And suppose now I want to perform an integral which involves the exponential distribution. Then clearly, what I need to do now is to make a transformation of variables from a uniform distribution to the exponential distribution, because my random number generators, they are actually set up using a uniform distribution. So another thing which we have to keep in mind when we are doing this operation, there is something which is called conservation of probability. You're probably familiar with conservation of variables like the energy, but probability is also a quantity which is conserved. And you will quickly see why. So if I now have a py dy, and then I have a new distribution, which is a uniform distribution, so I could now think of a p prime of x of d of x. So p prime is another distribution, and p of y could now be my exponential distribution. Why should probability be conserved? Any good ideas? There's a very simple explanation to that. So if you're dreaming of winning in the lotto, there is no magic transformation of variables which makes you a lotto millionaire, period. So the probabilities have to be conserved. So you cannot find a smart variable which increases your probability. That sounds logical, right? Because else we could have become lotto millionaires and we don't need to be here. So probability is a quantity which we simply postulate is conserved. So there is no kind of magic transformations which increases the probability. Okay, does that sound reasonable? So that's a basic assumption which we do here. So that means that with this assumption, I can now make a change of variables. So I could now define my p of x prime of d of x to be the uniform distribution. So let's just do that as an example. So uniform distribution. So which means that this is just d of x, and x here is defined between 0 and 1. If I now go back to my exponential distribution, my p of y d of y, which is equal to e of minus y d of y, then this has to be conserved. Now, y here is, as we said before, is defined to live between 0 and infinity. So what I need to do now is a mapping from 0 and 1 to 0 and infinity. And the way we would do this now is simply to integrate up here. So I would integrate the d of x from 0 to 1, and I integrate e of minus y from 0 to y here. So that means that my x as a function of y is simply now given by the integral from 0 up to y. And then I have my e minus y prime of d of y prime. I'm simply integrating up because my d of x goes from 0 to 1. And that means that if, I hope you don't get offended if I just make this step immediately here to here, right? So that's just an integral up to 0 to 1 and integrating up. And then I can find, and this is normally called the cumulative distribution. So when I integrate up, I know that this one is just 1 minus e to the minus y, which then means that I can now find an expression for y of x, which is simply given by minus ln of 1 minus x. And you see now that when x, that y is equal to 0, when x is equal to 0, because then I have ln 1, right, which is 0. And you see also that the y is infinity when x is equal to 1, because then we have ln 0, which is minus infinity. And then we have a minus in front of it, so that becomes infinity. Now, in general, your random number generator for the uniform distribution will never give you exactly 0 and exactly 1, but it will give you something very close to 0 and something which is very close to 1. So, but you see now the mapping which you can make. So I can now use my uniform distribution to generate the points x here, and then between 0 and 1. But then if I want the points distributed according to the exponential distribution, I need to make this mapping. So this is a change of variable. Now let's try to see what happens if I now look at another example here. So now I'm going to cook up a new distribution, which I just defined. So I've defined now a distribution P of x, which is given by 1/3 of 4 minus 2x, and x lives between 0 and 1. Now, this function here, which looks pretty innocuous, actually behaves as a probability. So if I take this P of x and integrate from 0 to 1, of P of x d of x, you will see now, if you do the math, that this is actually normalized to 1. Then what I'm interested in, so this is the probability distribution I want to use now. I will come back to why I want to use this one. Then my P of y, which I define here, B of y dy, is a uniform distribution. So this is the one I will use now to generate my random numbers. It's a uniform PDF. So that means that this y follows simply a uniform distribution. And y is also defined between 0 and 1. So just coming back to what I said previously, the random number generators are based on a uniform distribution. So if I want to use this new P of x here as my new probability, then I need to actually make a mapping from a uniform distribution to this new one here. Now, again, I can perform my integrations here, and I can find that my new distribution here is now given in terms of this distribution which we have. So I can actually find, if I integrate up again in the same way as we did here, if I do that, I can now find that my y of x, I can relate that one to this distribution there. And I can find that this is equal to 1/3 of 4 minus x times x. And you see now that when y is equal to 0, then x is 0. And you see also that y is equal to 1 when x is equal to 1. Because then we have 4 minus 1, which is 3, times 1, which is still 3, divided by 3, and that gives us 1. So I can now generate points according to the uniform distribution here. And with that, I can now find my x. So this formula here for x can then be used to, and I'm not going to do this, this can also allow us to find x as a function of y. Okay? You see these mappings? So why am I interested in that? And this brings us now to importance sampling. So why? So the reason for why we do this has to do with importance sampling. And I'm going to try to show you an example here. So that brings us to the next point. And now I'm going to look at an integral which is given by an integral from 0 to 1 of d of x of 1 plus x squared. This is a famous integral which has an analytical result, which is given by pi divided by 4. So that's a famous integral. Now comes an interesting point here. If you now look at this, so let's just call this as a function of f of x, d of x. Now, if you look at this integral, I can rewrite that one as an integral from 0 to 1 multiplied with that probability p of x of f of x. So I'm just inserting that probability of p of x of d of x. And this p of x is the function which I plugged in, which is this function 1 over 3 of 4 minus 2x. So why am I doing that? And so I'm going to do as we do in this kind of a TV series. I'm going to leave you guys in a suspension till after the break. So you cannot wait till episode number 2 begins, which is after the break here. But I'm going to give you a small hint here, and that is that what we are searching for is a probability distribution which makes this ratio here a constant, or almost a constant. Because if this ratio becomes a constant, which would be the ideal, you would put that outside, and then you would simply integrate the probability which has been normalized. So that would give you a constant times 1. Now, there's a very important aspect which comes in then. That is the variance of this stochastic integral. And that variance is going to be exactly equal to 0 if we can find a probability distribution which follows the function p of x. So this is the essence of importance sampling. But let's wait with that till after the break here. Okay, so welcome back. The topic now is to try to motivate a little bit the importance of importance sampling. So if you now look at this specific case we have picked out here, there is something particular with this probability distribution, which is very interesting. So the only thing we did was to rewrite this integral by multiplying with 1. And in our case, the interesting situation here, when we now look at the ratios between this function f at x equals 0 and divide with p at x equals 0. And you will also see that in these 2 endpoints which we have, this is actually equal to 3 over 4. So just a constant. So ideally, what we would like to have is that, so the kind of ideal, this the ratio between these functions is not going to be a constant between 0 and 1, but it's actually the same value between 0 and 1. So the ideal would be that we find a probability that this f of x divided by p of x is equal to a constant for all the x values which we are integrating over. For all x. Now, the way we can view this now is as follows. So what we have done is to rewrite the integral in terms of this 0, 1, and then we have a probability p of x, and then we have f of x divided by p of x of d of x. And now what I'm going to do is just to relabel this one, and I'm going to call this for a function f of x. So what we are calculating now is the expectation value of a function uppercase letter f. And this means that if this is a constant, if constant, then the integral is very simple, because then what we would have is that 0, 1, our integral is actually equal to p of x of this function f of x, which is now a constant in this domain, which we are integrating over. So this would just be equal to a constant multiplied with a normalization integral. And this is defined then to be equal to 1 because we have already normalized the probability distribution. So that means that this expectation value, the expectation value of f of x, is now simply equal to, which is actually defined as 0 of p of x now, of this f of x. That is obviously just a number, times this integration, this normalization factor. Now comes a very interesting property, which is a quantity which we will define, which we will need to use again and again. And that is the variance of a specific quantity. So if we have this variance of this quantity f of x, that is defined as the integral in our case of p of x, and then I have f of x minus its mean value, and this is squared multiplied with d of x. So this is just multiplied with d of x. Are you familiar with the definition of the variance? So this is again the same as us calculating p of x of f of x squared of d of x minus, and this is just the mean value squared of f. Now, if we are lucky and the ratio between this little f and p of x is constant, so if this quantity here is a constant, so if constant, then what we are getting then is that the variance is going to be exactly equal to 0. So if that is the case, then this will be 0. If that one is a constant, because then we are just going to get the constant squared minus the mean value squared, which is just a constant squared. So then we will get exactly 0. That means that we will, with a 0 variance, the standard deviation is also going to be 0. So with 0 variance, then obviously the standard deviation, and this is normally written STD, the standard deviation is also 0. So having 0 standard deviation is something which is a kind of ideal, because that means that we have calculated precisely the value of the expectation value which we're looking after. And we have essentially, so the standard deviation is a measure of the error of the calculations which we are doing. And you will see that everything we are going to do in this course will rotate around us getting a best possible estimate of the standard error or the standard deviation, which means that we have to calculate the variance. So the variance shows the spread around the minimum. Now, the ideal then is that we can find some kind of distribution, P of x, which makes this ratio almost constant. This is normally not the case. However, we are often trying to look after a probability distribution which follows our function. So the way we would typically rewrite that integral, if we find something like this, is that we, when we now look at the change of variables, so with a change of variables, so remember now that this specific function, which we picked in this example, this function p of x, which we chose here, this function has its own random numbers, which are generated according to this distribution. So what we would need at the end is actually to make a transformation from the uniform distribution. So we would actually need now a mapping from the uniform distribution, which we I did not put that up here. Yeah, so we would need something like a uniform distribution like this one, by which we could now make a mapping into this variable x. So we would need an x as a function of y based on this expression here. So we would generate now numbers, random numbers with a uniform distribution, and then we would have to map them over to x. So that means that if we now go back to this change of variables, which we need to do, then we have the uniform distribution given by this p of I, d of y, which then becomes just d of y in the domain where it's defined. And this is going to be equal to this distribution, which we called p of x, which in our specific case then is the same as 1/3 of 4 minus 2x of d of x. So that's the distribution which we have. And that means, again, that the integral which we had, this integral I, which we now rewrote in terms of this p of x multiplied with a function f of x divided by p of x d of x. If we now make the change of variables, this is going to be given by the integral from 0 to 1, in this particular case, of f of x as a function of y. So where y is going to be the standard random number generator, which follows the uniform distribution, and divided by this variable, this function p of x of y. And then it's multiplied with d of y, because now p of x, d of x is given by d of y. So this quantity which you see here, this one and that one, is now replaced by d of y. And this is our mapping into the random number generator. So what we end up doing now is actually calculating this ratio here. Now, the ideal is obviously that this function, which we are going to evaluate, this ratio, is a constant. Because if it's a constant, you will see then that the variance is exactly equal to 0. So why is this interesting? So let's look at a very simple example and try to gain some intuition about why important sampling is so important. One thing, I guess you see the basic overarching theme here, right? That we are stuck with a random number generator from the uniform distribution. We need to make a mapping, but we are also searching for a probability distribution, a new one, which follows our function. So let's suppose now that we are looking at a function which lives with x between 0 and 1, just for simplicity. And we want to integrate this function here from 0 to 1. So we want to calculate this specific integral of 0 to 1 of f of x of d of x. Now our function is just defined between 0.4 and 0.6, and it may look like this. Okay. Then, so this is f of x. But then I also have my uniform distribution. So let's suppose 1 is here. So the uniform distribution looks like this. So this is my P of X, the uniform distribution, which is now given by this letter U. So there's no unique symbol for the uniform distribution, so I'm just introducing a letter U here. Now, if you now pick your points with a uniform distribution, suppose now you pick 1,000 points. The uniform distribution will now give you, if we look at this domain we are interested in, so if I take 1,000 points, so in total I have Monte Carlo samples equal to 1,000, but now you see that only 200 are in X from 0.4 to 0.6. So that means that from a computational point of view, since this integral is going to be approximated with 1 over m, and then I have a sum from I equal 1 to m of f of x of I. So if you look at this integral, what happens now is that you're going to waste 80% of the cycles, because the function is going to be 0 in all other points except between 0.4 and 0.6. So you see now the reason why importance sampling is so useful. So if I now can find a probability distribution, so the strategy here would be to find a probability distribution which perhaps follows this function here, something like that. So this function looks like a Gaussian. So if I could define a Gaussian between 0.4 and 0.6, then I would make the mapping from 0 to 1 to 0.4, 0.6. In that specific case, that means that of the 1,000 points which I would pick, I would have 1,000 points in this region here only. And that means that when I evaluate this final sum, I would not be wasting cycles. Does that sound reasonable? So the ideal here would be to find, in this specific case, so we would, the ideal, find a PDF, and I'm going to call this P prime of some y, with y which is defined between 0.4 to 0.6. That's where the function is non-zero. So where f of x is non-zero. So this is what we would call the change of variables. So that's the first step, change of variable part. Okay. Then the next step, so first we find a PDF where f of x is non-zero. Then have a PDF that f of x divided by p over, so now we would have f of y here, of f of y is close to a constant. In that case, in this case, and this is called the importance sampling. We are sampling over the important points. And the benefit here is that the variance of this function f is going to be close to 0 or small. So this is why instead of us having a random walker which jumps according to the step which we fixed, where we can actually end up in regions where the function is 0, we are now trying to sample these points according to where the function is non-zero. In that case, we are sampling over the important points. So important sampling means you sampling over points where the function you want to integrate is non-zero. And hopefully, to find a function so that you can reduce the variance. And this is one of the holy grails of Monte Carlo calculations, to find through some engineering tricks. So there, what you do then with importance sampling is something which actually follows the function you want to integrate. So there's a lot of kind of engineering in order to find such a probability distribution. If you can do that, then you can have a variance which is pretty small. And that's the kind of holy grail when you do Monte Carlo integration. To get a small variance and not to waste cycles. So with this kind of long detour, this is actually meant as a kind of overarching view on why importance sampling is so useful. That sound clear? Any questions? So if you want to, you can play around with that simple function. And you will also see that if you calculate the Monte Carlo integral for that simple function, that is going to be pretty close to zero. You're going to have a variance pretty close to zero. Compared to if you were to perform the integration here with a uniform distribution, because then you would waste a lot of cycle in regions where the function is not different from zero. And also you would have a ratio here, or an f of x here, which is not optimized or with a probability which follows the function itself. Okay, so these are the two important steps: change of variables and what we normally call importance sampling. Okay. So one thing I wanted to say a little bit about now, before we go back to a little bit examples and also the calculation of the Langevin equation and the Fokker-Planck equation, which will be the topic for next week, I wanted to say a little bit about the choice of a trial wave function and why they have these specific forms. Now, one thing which is simple for us in project one is actually to say that we know that this is a harmonic oscillator when we take away the interaction. We are placing particles in a harmonic oscillator, and then we have the solution or the ansatz for the trial wave function. So the question is, can I find an ansatz for the trial wave function without too much information about the physics of the system? So what is a general strategy for finding an ansatz which has some minimal requirements? Now, for the harmonic oscillator, we have actually baked in the minimal requirements already. So let's now look at this part here, because this brings us back to the example which you will see at the end of the lecture when we're going to run codes now. So the ansatz for the trial wave function, this is a very delicate thing. In project number 2, you can replace the trial wave function with a neural network, and you will see that that is going to give pretty good results. But the question is, can we guide the Monte Carlo optimization with something which has some minimal requirements on the wave function? So let's now look at the basic strategy for doing this. So this local energy which we're having is now defined as 1 over the trial wave function. And now I'm skipping the variational parameters here, if that's okay, just for the sake of simplicity. So this is something which depends on the positions of all the particles. And then we have a Hamiltonian, and I'm putting a hat because this is an operator which is acting on the system. Now, let's now look at a simple case. So, and this could be an electron in hydrogen, in atomic hydrogen. Here we know that if we use spherical coordinates, we can find the analytical solution. Now, this analytical solution, when we look at it, so that means that the wave function in spherical coordinates and this is just a quick reminder, what we have then is that the solution to the problem is given by the quantum numbers n, the number of nodes the wave function has, and the angular momentum. And this is a function of r, the radius, this in spherical coordinates, the angles theta and the angle phi. So r is then defined from 0 to infinity. The angle theta is defined from 0 to pi. And the angle phi is defined from 0 to 2 pi. I hope this rings a bell. This is just back to basic quantum mechanics. One of the first cases you solve after the particle in the box is the hydrogen atom. And this has a wave function which then depends on Rn and L. There's a radial part. And then we have the spherical harmonics, where we have an additional quantum number, which is the projection of the orbital momentum, theta or phi. Okay? Now, we are now going to focus on the radial part only. So if I now look at this local energy operator, which I have, so my Hamiltonian then is just given by the kinetic energy plus the attraction from the atomic nucleus, which just has one proton in our case. And the charge is equal to 1. So let's now look at the, as a quick reminder here, let us now look at the Hamiltonian of the system. So the Hamiltonian in atomic units, where I put the mass equal to 1, h bar equal to 1, and c equal to 1, etc. So these are called atomic units. Then we have that h is given by minus 1/2. So I'm putting h bar, the mass, c, etc. equal to 1. So I'm going to have this one minus, and then I have charge 1 divided by r. So this is the attraction from the atomic nucleus. I hope that also is something which I've seen before. So when I look at the function now, this wave function in or the local energy. So let's now look at the local energy for the radial part only, because that's the case which is going to be tricky. And the reason why it's going to be tricky is that we have a term which goes like 1/r. So we know now that when the wave function goes to 0, no, when r goes to 0, we have a divergence here. Okay? So we need to find some properties of the wave functions which cancel that divergence. And we know that the energy is a finite quantity. So let's look at the local energy for the radial part. So that is going to be given now by an E of r. And now I'm just writing r here because I'm getting rid of the angles. So I'm not looking at the angle part because they don't give rise to any divergence. And the reason for that is that the divergence I have comes from this one. And it comes, so I'm just putting the radial part. So this is now going to be r. And I put a t here because that is a trial wave function. So I'm assuming I don't know anything of it, except that I want to find some minimal properties. And now I'm looking at everything in radial coordinates first. So this is going to have, when I write out the derivatives in spherical coordinates, it's going to have a second derivative with respect to r. But then there is also a first derivative. There is a r. I don't know if you remember that when you rewrite your second derivative in Cartesian coordinates to spherical coordinates, you get second derivatives with respect to the angles. They don't cause any problems, so they will give a finite expression. So we can only focus on the radial part. And then there's a minus 1/r, and this is multiplied with RT of r here. And then we have plus, and now I'm adding in here all these finite terms. And these finite terms, they will depend on the angles theta and phi, and they don't give rise to any divergence for us. So we can just leave them out because what we need to think of now is the limit when r goes to 0, because there are two clear divergences. And you see now that when r goes to 0, there is a divergence here, and there is a divergence here. So these two guys here are the things which we need to worry about. The other terms, if you now remind yourself about some of the properties which we require on quantum mechanical solutions, is that the derivatives of this R of t, of dr, are equal to a number L, which is smaller than infinity. So it's a finite quantity. We know that the kinetic energy is a finite quantity. The total energy of a system is a finite quantity. So these quantities cannot diverge. So if you go back to some of the basics of the mathematics of the solution of Schrödinger equations, these are conditions which we impose on the derivatives and thereby on the wave function. Okay? So that means that the terms which you see here with the derivatives, they are going to give us a constant in that limit. So the derivatives do not give rise to a divergence. It means now that when I look at the limit, when r goes to 0, it means that this term which you see here is going to be a constant. So the two terms which we need to look at are actually these two terms here. So what I need to be careful with then is that in the limit of r goes to 0 of the local energy of EL of r, there are actually two terms which we need to take care of. And one, so we have 1 over RT, and then we have minus 1 over R of d dr minus 1 over R multiplied with RT. And these are the two divergences which we now require that they cancel. So this means that this one is a quantity we want to get, plus we have some finite terms. So we should act, so we want this one, and I have omitted here, that's a little bit sloppy mathematics, omitted finite terms. Now, if you then look at this equation which you have here, this equation, so if we take that one, that means that if we want to drive that to 0, this simply means that they have 1 over R of d dr of RT, the trial wave function, is simply equal, when we now do the mathematics here, this is simply equal to 1, or actually RT here. So this is going to be equal, no, sorry, there's not an R here. Sorry, I actually wrote this wrongly here. So this is minus RT. And this has a solution which we know pretty well. So this means that the minimal form of this RT is e to the minus R. So if you remember, yeah. So what you have here is 1 over R. 1 over R. Yeah. Because you have a factor, the factor here comes here, the 1/2, from the second derivative here. But then when you are in 3 dimensions, there is a factor 2 which cancels the factor 1/2 when you write it out. So this expression which you see here is the radial part of this one when you move from Cartesian coordinates to spherical coordinates. So you have 2 divergences. So one way to require that the solution should give you finite energies is to require that these 2 divergences cancel. And that gives this minimal shape. So we would call this the minimal form, minimal requirement. Now, you may remember that when you solve these equations exactly, you will find that this RNL of R is actually given by e to the minus some constant alpha times R multiplied with the so-called Laguerre polynomials. And these are polynomials which depend on n and L. So these are called Laguerre polynomials. So this minimal requirement doesn't give us these functions, but it gives us this shape. So when you look at the solution of the hydrogen atom or any of these atomic systems, what you will find then is that this minimal requirement, which you have on the wave function, that guarantees that these two terms cancel in the limit when R goes to 0. Then you obviously have conditions on when R goes to infinity, etc., which you can bake in. So this is one way by which you can make an ansatz for the trial wave function. That sound okay? So you use actually the Hamiltonian to find an ansatz for the way the wave function should look like by requiring that the energy should remain finite. And that means that these divergences have to cancel. Now I can do the same thing when I have two electrons which are getting close to each other. You will get a similar equation, but then you would have to rewrite the two-body kinetic energy in Cartesian coordinates to spherical coordinates. And when you do that to spherical coordinates, you would have to separate the motion in terms of the relative motion and the central mass motion. And it's a relative motion which gives problems. So let me just mention this because you would repeat the same exercise. So when we have for potentials, so one thing is on the single particle piece of the wave function, for potentials like the Coulomb repulsion between two electrons, then you would have something which looks like 1 over, let's say, R1 minus R2 here. And there you see that when two particles are getting close to each other, then you can have a divergence. Now, that divergence will again be cancelled in a divergence in the two electron kinetic energy. So you can take the two electron kinetic energy and rewrite that in terms of the relative motion, because this quantity here is nothing but the relative distance, and the central mass motion. So the kinetic energy is an operator which you can rewrite easily in these new coordinate systems. Then there will be a path which will depend on the central mass motion, which doesn't diverge when two particles are getting close. But then there will also be a path which is going to have a 1 over R1 minus R2. So this term is nothing but 1, and if we are in 3 dimensions, this is going to be given by x1 minus x2 squared plus y1. So this is in Cartesian coordinates, plus a z1 minus z2 squared. Now, for a two-body problem like this, for two particles which are getting close to each other, getting close to each other, which means that we have a limit where R1 minus R2 goes to 0. And in that specific, in that specific case, what we have is there is a term in the kinetic energy in relative coordinate or relative motion kinetic energy, which cancels the 1 over R1 in the potential energy or in the Coulomb potential here. Now, since this term, when it's a repulsive, it comes with a plus sign. So if you look back at what we had here, for the atomic hydrogen, the electron gets attracted by the proton in the atomic nucleus. Now, when you have a repulsion, there's going to be a plus term here. And if there's a plus term here, that translates into plus term here. So in that specific case, there will be a minimal requirement in this case, that means that we need a RT for R1 and R2, which is proportional to some constant beta multiplied, and I'm going to write a code as R12 here, where this R12 is just R1 minus R2 here. So there's a minimal requirement on the wave function in order to cancel these divergences. So there will be a divergency at the one particle level, but there will also be a divergency at the two particle and many particle levels. So when two particles are getting close to each other, there is a divergency, which then gets cancelled by a divergency in the kinetic energy for two particles. And that leads to a minimal requirement on the wave function, which looks like that. So if I now want to use this to make an ansatz for atomic helium, so an ansatz, a minimal ansatz for atomic helium, so 2 electrons. So that is a minimal ansatz, is that I have a trial wave function psi of t of R1 and R2 here, which is proportional to E to some parameter for R1 plus R2. That is normally called the one-body part, one body, because this takes care of the divergence which you have from the atomic nucleus attraction. And this is then multiplied with a term here, which has a minimal term with R12 here. And this is normally called a correlation part because it takes into account the correlations between two electrons. So this is the correlated part. In general then, what you will have, so if you now replace this system, so this part is also called the Jastrow function or the correlation part. And the other part is just called the one-body part. So these two minimal conditions on the wave function that you cancel these divergences, that gives you an ansatz based on your Hamiltonian for the system. Now, in the examples which we will discuss next week, which are also in the codes here, so you will see these things again next week, we are looking at a harmonic oscillator for 2 electrons. Electrons in 2D. So that means that we are going to have something like this. This is a very nice system. So the ground state would be a system for the harmonic oscillator where we have nx and ny equal to 0. So we would have 2 electrons here. One will spin up and one will spin down. That's an ansatz for the ground state. Now, in that case, the one-body part would now be replaced by a harmonic oscillator. But you could have a two-body part, the correlated part, which runs like this term in order to cancel the divergency in the two-body interaction or the two-particle interaction. So for this specific case, you would then have an ansatz of psi of t for R1 and R2 here, which looks like e to the minus alpha squared, which since we have the harmonic oscillator, R1 squared plus R2 squared. These are the positions of the two particles. So R1 is simply EX, the unit vector, times X plus EY, the unit vector in the Y direction, if you stick with Cartesian coordinates. So this will be the vector R1, and then we have a 1 here and 1 here. These are the positions times the unit vectors. So when we square it, it's much easier because these are scalar quantities multiplied with a beta times R12, where this one is the relative distance. Now, these two parameters, which you see here, they are the variational parameters. And this is what my code is actually calculating. But we will discuss that a little bit more in detail next week, when we also now go through the Fokker-Planck equations and the Langevin equation and discuss the derivation of that specific transition probability. So today, the aim was more to give you the setting, why we do importance sampling, because obviously we want to calculate these integrals. If you go back to this very, very simple example here, we want to have some sampling where we actually are following the function we want to integrate. Because else, if we just do this in a brute force way, we would then be sampling points where the integrand is equal to 0. And we also want to have a probability which we are sampling after, which makes the ratio between the function we want to integrate and the new probability close or constant. In that way, we will have a little spread as possible of the expectation value. So that means we drive the variance to as close to 0 as is possible. So these are, when you do Monte Carlo calculations, you always have to give the error, which is the standard deviation. And everything in Monte Carlo calculation rotates around you finding some smart tricks to reduce the error in your calculation. And the error is the spread of the mean value. The smaller that spread, smaller the standard deviation, the happier we are. So there's a lot of kind of, engineering tricks in order to reduce the standard deviation in Monte Carlo calculations. And one of these is importance sampling, which has also the benefit that we reduce the number of wasted cycles so that we sample our random jumps in space, follow the function we want to integrate. So the other thing which I just wanted to give you a short motivation for is how we actually arrive at the shape of the trial wave function. When you replace this with a neural network, you will often see that the neural network is able to find this kind of minimal requirements by optimizing the Hamiltonian. But it needs a guidance because there are symmetries which are not baked into a neural network. So everything you do when you solve a physics problem like this, you need to bake in some insights about the physics. So even if you use a neural network and that functions as a universal approximator, you will see that you need to tell it what kind of symmetries the problem has. Because the network could find the symmetries, but you would waste a lot of cycles to find the optimal representation. So if you can put in some physics, you can then guide the optimization in a much better way. And in principle, this is what we are doing here. We are actually baking in some physics information, some minimal requirements on the form of the solution. And when we do a Monte Carlo integration with this form, we will not have the exact solution, but the hope is that this form here is closer to the exact solution than another form. And at the same time, we get rid of divergences, because if we don't have that specific form, we may easily actually have something which gives us 1 or 0 here. Okay, does that sound okay? Should we move to the lab sessions? And if that room is available, we just use that one. If not, we have the big one. That's it. So I'm going to stop the recording here.